Yes, please talk with you.
Yeah, I'm sorry for the delay. Computer had a problem. So before I just want to switch gear and talk about Alaska subduction zone. Before I begin, I would like to thank Dr. Sang-Wook Lee and organizer for giving me a chance to speak about my research at Lamont. And also I'd like to acknowledge my postdoctoral advisor, Jeff Abers. And in addition to my co-authors here, I would like to also acknowledge a large number of people who contributed to the field portion of the seismic arrays deployed in central and southern Alaska. Currently, shallow or flat subduction occurs in 10% of subduction zone worldwide, and seismologists are trying to understand different dynamics and properties of the subduction system by carefully analyzing seismic signals recorded from the seismic station. And certainly I'm one of them, and I'm very interested in flat slab subduction. And today I'd like to show you some of our preliminary results for the Alaska subduction zone based on the array data sets in Alaska. And today also I'd like to present slab geometry and also discuss their relation to slab seismicity and their interplay coupled zone associated with 1964 Great Alaska earthquake. So Alaska is one of the places where we can study flat slab subduction along with very complex crustal structure due to a series of terrain accretion along with the large-scale strike-slip fault system in the continent. But there seems to be even more growing interest in Alaska because U.S. array transportable and flexible array will land on Alaska in 2014, and still the TA station locations are being in discussion up to now, but there's no doubt that in near future we will have high-resolution 3D model for continental crust and a mantle for Alaska at much larger scale, like we currently have for Western U.S., a model for Western U.S. Based on the TA data set. Just briefly discussing the tectonics of the area. The Aleutian subduction system terminates at the Gulf of Alaska, and the subducting plate underneath southern Alaska has been inferred to be quite shallow at depth less than 50 kilometers, leading to one of the widest interplate threat zones. Southern Alaska is tectonically a very complex area because the crust was formed by a series of terrain accretion, and the continental crust has this large-scale strike-slip fault system. And as you might imagine, southern Alaska is seismically very active, and the intense seismicity is mostly from an interaction of downgoing oceanic Pacific plate and overriding North American plate. And the notable earthquake is this 1964 Great Alaska earthquake of moment magnitude of 9.2. And I just shaded the 1964 earthquake rupture zone. This area has been constrained by the aftershock distribution. So here, the area just south of the border ridges fault can be characterized by high and steep mountains, and this sits at the northern boundary of subducted portion of the Yakutat terrain. So here I only highlighted the unsubducted portion of the Yakutat, and so this exotic terrain is in the process of accreting onto North America. And this Yakutat terrain with 25-kilometer packet of mafic rock has moved north with Pacific plate, and it begins to collide to North America at 6 million years ago. And there is still ongoing debate regarding the nature of this Yakutat terrain, whether this is a combination of continental and oceanic crust, or this is just one piece thick oceanic crust. But in either case, it is buoyant and resists subduction into the deeper mantle here. And what's clear is this collision of Yakutat terrain is likely to contribute to first the shallow plate interface in this area, gap in volcanic arc. Second, drives mountain building process up to 500 kilometers inboard of the plate boundary. And third, exerts major controls on interplate thrust processes in this area. And lastly, it becomes the site of the 1964 earthquake. In particular, as in the case of earthquake slip direction, the dip of the plane on which the rupture occurs during the 1964 earthquake is not being well constrained based on the unknown plate geometry and also the presence of Yakutat terrain. So we use two different array data sets in southern and central Alaska. So Moose here and Bear, and though these stations have been operated in two different time periods, so we use this array data set to image the subduction structure. So some of the key questions to investigate is, first, what is the geometry and velocity structure of the downgoing plate, in particular their relation to slab seismicity and metamorph evolution, pattern of mantle flow, and fabric associated with slab edge subduction. And secondly, what is this 3D structure of the subducting Pacific Yakutat slab in the Coconut Basin? Based on the GPS vectors and seismic tomography, the western edge of the Yakutat terrain lies somewhere here. But we don't have at the moment we don't have a good constraint on that, so we would like to provide better, more tighter constraints on the location from our data set. And also the part of the subset of the boost stations co-located with GPS sites cover part of main asperity of 1964 earthquake, so we would like to use them to carefully examine the properties of subduction zone megathrust fault. So here I'm showing the seismicity of the area, and as you can see, it's seismically very active, and I color-coded with depth of the earthquake, so the depth increases this way toward the direction of the Pacific plate. And I just reduced the size of the earthquake and plotted the non-volcanic tremor location, and tremors have been identified at the northern part of the Moose array, but these has very poor depth of resolution, partly because of the insufficient station coverage. So this subset of the so these earthquakes has been recorded from this Moose stations, and all subset of this data set has been relocated, and I'll be showing them in upcoming slides. So here I'm showing the relocated seismicity, and relocation was done by double difference. And first I'm examining the more east-west profile here, and the result shows in this panels. And so the Pacific plate is dipping quite steeply here, and beneath the Kenai Peninsula, we see a nearly flat, nearly horizontal plate interface, even though some of the earthquake locations are quite sparse. But such flatness can be seen more clearly if you look at more northwest profiles. So the point I want to make is, in this subduction zone, seismicity alone provides pretty good constraints on a plate geometry, unlike Mexico subduction zone. So here we used teleseismic P2S converted waves to image the subduction structure. So this method removes source-related and mantle path effect by deconvolution, which greatly enhances PS conversion as well as reverberated phases associated with any structure beneath the receiver. So basically, you can compute the receiver function from one source and receiver pair, and you do the computation for all the stations, and later you sort the receiver function by station and stack them later to further reduce the noise level in the data. So here I'm showing the stacked receiver function. So we use this red square stations here, and then we already projected our response to the AA prime here, which is a down dip direction. So the azimuth angle is 30 degrees from the north. So let's just stare at this data. We see this prominent arrival at the 0 second corresponding to P arrival. And basically you look for the consistent arrival at later time. And they are this negative and double positive peaks. And I just translate this signal into this, translated to a more simpler diagram. And in order to have this negative and double positive peaks, you need at least 2 low velocity layers. So, and I'd like to draw your attention to this very prominent negative arrival, and this represents the reduction in seismic velocities. And I plotted the relocated seismicity onto this image, and the seismicity is between this negative and first positive peak, and so relocated seismicity are here in the first low velocity layer. And this prominent peak suggests that maybe this is due to the large amount of trench sediment or high pore fluid pressure, or maybe the combination of those 2 factors. So we attempted to provide the P wave and S wave velocity along with the density by finite difference modeling, and I just want to quickly go through. So basically, you you group the residual function by different Black-Azimuth group and the rate parameters, and you basically stack them, and then compare with the synthetic. And synthetic was generated from this simple model that, like I showed before. So you basically need crust in a 2 low velocity layer and an oceanic mantle. And this model has been carefully selected so that this can fit that negative and double positive peak, as well as the later arrivals. So this is the VPBS model, and this top low velocity layer has high VPBS of 2.0, and like I suggested before, maybe high pore fluid pressure or a large amount of sediment may contribute to this large high VPBS ratio. And the thickness has been also constrained, and the thickness is about 5 to 7 kilometers. And I'm providing the lower boundary of the number. So if I do the sensitivity, this thickness can go up. The thickness can be smaller, but we get higher VPBS value. So in addition to this converted phase analysis, we also did the migration based on a multi-channel recording of scatter energy in a coda of teleseismic P wave. And so this method uses reverberated phases in addition to converted phases, and so one can obtain better resolution by factor of 3 relative to the direct conversion because of the longer delay time in given interface depth. And we try to use the earthquake sources occurring wide azimuthal distribution to eliminate the subarray structure as completely as possible. And as I showed here in the figure, seismic energy is stacked along the different hyperbola to convert to a depth of scatter for each recorded phase. And later we sum the different individual contribution to form an image. So this is just the setup. So we use the subset of Moose and Bear Station and projected onto AA prime, and these are the source locations. So I'm showing the individual mode contribution. So here, just for a reference, I put the seismic rate path diagram. So basically, you get P wave perturbation and then S wave perturbation image. So just let me explain the color scheme. So basically, what you're seeing is P wave and S wave perturbation with respect to a smoothly varying 1D velocity model. So here we get 1 P wave image, and then we get 4 S wave, and you stack these with different weights to produce this one composite S mode. So I just pulled out this P wave image and S wave image, and please note that this has much lower resolution than this because P wave has this one seismic mode. So we only use this P wave image just to confirm the structure. So we mostly put more emphasis on the S wave image. So if you look at this one, so this is Moose, and then the image as subductive structure beneath Bear. Now let's just focus on the Bear part. So we see very thick crust subducting into the system. And previously, Jeff Avers and others proposed that the yucca terrain subducting into the system, and that explains very high topography in the upper plate. And this is the moho. And let's focus on this middle part. This is more complicated. We see sudden increase in the dip and the velocity, and also the thickness, where we see this non-volcanic tremor. The depth has been not so constrained, and also we see increase in seismic activity where the slab is dipping. So this part is smooth. And we see very thin layer. We thought that we would image very thick crust, but what we're imaging is this thin megathrust layer. So some of the seismicity in this layer has the thrust mechanism, so that gives strong indication that this is a megathrust layer. So let's just look at the different profile. And so we have this is using just boost stations, and we have this very thick sedimentary basin called Cookinglet Basin, and so the basin that's changes from 0 to 7 kilometers. So this is by receiver function image, and as you see, seismic energy gets trapped within this basin, and so we get very complicated peel arrival. So you cannot really see this subtle signature from the downgoing Pacific oceanic crust. But certainly this is modelable. So my next step is to model this area to pin down the location for Pacific oceanic crust. So the edge is suggested to be here based on the tomography by Eberhard Philipp et al. In 2006. And so this is our migrated image. So we use this move station projected onto BB prime. And even though the responses beneath this Cookinglet basin is very noisy, but this method really clears everything up, and we were able to see this downgoing Pacific plate quite clearly. And these dotted lines are the relocated seismicity. And another interesting thing is we were able to image the western edge of the subducted yucca terrain. And they lie more east of this 1964 rupture zone. And interestingly, it's more closely related to this lock zone estimated from the inversion of the GPS data set. So this is the Eberhard Phillips location. So this is just a summary. I have these two striking image. So one of the image is this mega thrust layer, and we need to obviously compare our velocity with the field measurement. There's a velocity information at the Kodiak Island in Alaska, and we would like to compare our result to the field measurement as a future work. And another finding was that we were able to, for the first time, we were able to image this this western edge. And obviously, the seismic signals are quite noisy because of the Cookinglet basin. But I hope we could do more analysis on the receiver function. So I would like to model the receiver function to further enhance the image of this Yucatan Pacific margin. Thank you.
Okay, thank you very much. Any questions, comments? My question.
Yeah.
Can you show me the cross section? Oh, this one. 14th one. The 14th slide.
14.
You show the cross section T and S wave.
14.
And when you plot the seismicity,
Yes.
what's the range? What's the width of the seismicity?
Less than 20 kilometers. So I draw the circle around the station and then project it onto the projection line.
Okay, so you have a deeper events.
Yes.
Separate from the main zone.
This one.
That's a double seismic zone kind of thing.
I don't see the double seismic zone in this area.
But how are the events deeper? So about 40 kilometers.
40 kilometers.
Is that reliable?
We need more seismicity to.
Okay. Also have an event above between.
So this is crustal. And
it's a green circle.
Oh, so this is relocated seismicity from Bear Array. And
Okay.
it's quite interesting that it stops where at the 130 kilometer depth. And
No, I mean you need to pay attention to the even the here
this one,
and here.
this one.
Are they reliable or not? If they're reliable, they should be quite important. Otherwise, you should.
I think they're reliable because I picked a very close earthquake.
Okay. Thank you.
Yeah.
Any other questions? Comments? Yes, Margaret.
Yeah,
Can you yell?
yeah, I can try. How do these locations compare to the Geophysics and Mantle 2002?
Oh, actually, we agree
Can you repeat
with.
the question?
So I cannot pronounce the author, the name, but other Alaska group has relocated the earthquake, and they have an earthquake catalog. So I compare our seismicity pattern and also our image with their study, and we quite agree with each other very well. It's just like a less than 5 kilometer difference in depth.
And your study complements theirs in that you can go shallower because they cut it off at a given depth. You can actually shallow, like image the interface better. So
Right.
that's very complementary.
Yeah.
Okay, I see. Yeah, okay, Dr. Lee. A quick question.
You can imagine that the earthquakes are distributed mostly in the low velocity zone.
Yes.
Remember that in the morning, your figure has shown us the earthquakes are located mostly in the high velocity or around the boundary between the lower and the high velocity anomaly. So how can you interpret it?
So in this subduction zone, we see the seismicity is within this low velocity layer. So this is interplate seismicity. And then we see the same thing in here, and that's why we are calling this layer mega thrust layer rather than something else.
I think this is a good point. And
Yeah.
the same. Here, the earthquakes occur at the subducting moving across on the top of the slab. But in Japan, we also have a seam lowest layer on the top of the slab. But just because of resolution tomography, we don't show that. Okay, the resolution problem. Okay, but the lower plane of earthquakes should occur in the higher zone in the central part of the slab. Yeah. I think we have to move to our next talk. Thank you very much, Dr. Kim.